This is the Mathematics Education Podcast from mathedpodcast.com. Welcome to the Math Ed Podcast. My name is Sam Otten from the University of Missouri, and my guest today is Richard Cangelosi from Washington State University. Richard, thanks for being here.
Thank you for having me, Sam. It's a real pleasure.
So, Richard has the distinct pleasure of being my first doctoral student guest on the program. He's a PhD candidate at Washington State University, so congratulations on having this article out as first author before you've even finished your PhD.
Thank you, Sam. It's really exciting. I know that in the education field that publications are so important, so this is very special.
So we're going to be discussing Richard's article, which is appearing currently in Volume 32 of the Journal of Mathematical Behavior, and it's entitled The Negative Sign and Exponential Expressions, Unveiling Students' Persistent Errors and Misconceptions. And this is co-authored with Madrid, Cooper, Olson, and Harder, so I want to acknowledge them as well. But of course, you do nice work leading this up. So this comes from some of your work in graduate school, so I was wondering if you could just tell us about your graduate school experience and then help us see where this study came from.
Yes, so I guess I have to label myself first as a non-traditional graduate student due to my age. You know, before becoming a grad student at Washington State University, I'd already had a master's in applied math and had been teaching virtually full-time for about 10 years. And so when I came here, I spent a year or so trying to decide exactly what I was going to do. I started working with David Wolkind, who works on pattern formation problems, mainly in ecology. And in particular, we're working on a problem that deals with spontaneous self-organization of muscles in forming muscle beds. And when I say muscles, I'm referring to muscles marinara, not Arnold Schwarzenegger. But I always had a very strong interest in teaching and being a more effective teacher. So in addition to the PhD in the applied math area, I'm also pursuing a master's in mathematics education under the guidance of Sandra Cooper. And frankly, this is becoming a little bit of a monster because with my interest in math education, I thought that it would also be advantageous to learn a little bit more statistics, so I've added a minor in statistics. So I could have been finished, however, it's going to take about another academic year to fill in these other pieces.
Well, it sounds like quite a bit of ambition and quite a bit of thirst for knowledge. Which, you know, thirst for knowledge is a good trait to have for a researcher because that's really what we're doing, you know, forming these questions and really seeking answers to them. So in your master's work in math education, you started investigating this issue of exponents and exponential reasoning. And so I was wondering if you could just tell us where that interest came from, where the motivation came from for pursuing that exponential topic.
Well, as I mentioned, you know, I've been teaching for good 10 years or more. And through that experience, I had the opportunity to teach a broad range of courses from college algebra through the calculus sequence, differential equations, and many others. And then when I came to Washington State University, I received support in 1 year as a National Science Foundation Fellow. And through that fellowship, I had the opportunity to work with high school students. And through presenting projects and working one-on-one with these high school students, I was surprised to see similar errors being made by both the high school students and university-level students when working with certain exponential expressions. And so the genesis of the study was really wanting to investigate this anecdotal evidence in a more formal setting.
Okay. And so in what setting did you then decide to go ahead and try to really systematically explore this issue of the errors with exponential expressions?
So first of all, in particular, what we were trying to do is, one, address the idea of, well, are there truly persistent errors? And by persistent error, what we mean is there an error that students continue to make as they progress through a certain sequence, whether it's college algebra, pre-calculus, calculus 1, calculus 2, and so on, or just a pre-calculus, calc 1, calc 2 type of sequence. Mm-hmm. And so what we did is, at WSU, we constructed an assessment for students to take, and we asked instructors who were teaching college algebra, pre-calculus, calc 1, and calc 2 if they would be willing to allow us to come in and ask their students to participate. And as it turned out, we ended up with 904 students, which was a little bit unwieldy. So out of that 904, what we decided to do was randomly select approximately 100 students from each of the 4 courses. So approximately 100 from college algebra, pre-calculus, calc 1, and calc 2. So we had a little over 400 assessments that we were working with.
Okay.
And then what we did is it was a very painstaking task of going through the assessment, which readers or listeners can find in the appendix of the paper, and to try to categorize the types of errors that we were seeing. And it was through that categorization that we began to see that, yes, there was a couple of questions on that assessment that were being made across the spectrum of courses. Then what we did is we decided that, it's great to have this quantitative data, which basically we considered to be an indicator of a persistent error. And then what we wanted to do was then get one-on-one and have students meet with us one-on-one through a short 20 to 30-minute interview where they resolved problems that were similar to those that we identified as indicators of a persistent error. And we had about, I believe, 18 or 19 students participate in the interviews.
Okay. So we've got the 4 groups of students. They took the assessment, and then you selected this subset to conduct the interviews with to get some qualitative data to help you unpack what you were seeing in the assessment. And just to make sure that we have a vision of what these students are doing, could you just say a little bit about your assessment and what kind of items were included on that assessment?
So the assessment was split up into 3 broad categories. In the first part of the assessment, there were 8 questions which basically asked students to simplify a certain exponential expression, and that exponential expression could have contained a rational number or an integer type of number. They were basically unary expressions, meaning simplify 2 raised to the negative 3 power. Mm-hmm. Then there was a second part where students were asked to compare 2 exponential expressions using one of 3 relational operators, those being less than, equal to, or greater than. And then the final part of the assessment was simply to label an exponential expression as being positive or negative.
Okay. I'm speaking with Richard Cangelosi from Washington State University about his article in JMB. So you mentioned that you did find some errors that persisted across the groups of students, so the college algebra, the pre-calc, calc 1, calc 2. But I should mention, too, from the paper that you did see improvement on the overall performance, so the students were getting better at their work on this assessment as they progressed through the sequence of mathematics courses.
Yeah, that's correct. And what I find kind of interesting about the statistics that we collected is if you look on Table 2 of the paper, there's a place where we show the percentage of correct responses to the questions in the 3 sections of the assessment. And if you look at a question like A7, which is the first section, number 7, where students were asked to simplify an expression of the form 4 raised to the 0 power minus 4 raised to the negative 1 power, what we found is that only 17% of college algebra students were able to simplify that correctly. But as you go through the progression of courses, by the time students were in Calculus 2, 71% were answering that question correctly. So we did not consider that to be a persistent error.
Right.
However, if you look at an expression such as given in number 4, A4, there students were asked to simplify the negative of 9 raised to the 3/2 power. And there what you see is that in college algebra, only 14% of students are answering that correctly. And when you get all the way up to Calculus 2, still only 29% were answering that or simplifying that expression correctly.
Okay. So you're seeing some general improvement, but you're also seeing a few things that are persisting all the way through your data set.
As a matter of fact, we try to answer this question. We try to delineate the responses in a more rigorous statistical way by comparing proportion means. But when you do that, virtually everything comes up as being significant, as showing significant improvement. But then you have to step back and ask yourself, well, when you look at basically a high school question and only 29% of university level Calculus 2 students are answering it correctly,
right,
is that really progress? Are students really mastering it?
Right. Yeah, I think, from a practical level, that does seem problematic. And the article, you do a nice job of really digging into those, what you've identified as persistent errors. So I wonder if you can just tell us a little bit more about, what you found to be the persistent errors.
The interesting thing was that when we went into this study, what we expected to be problematic turned out not to be. And by that I mean we were really expecting expressions that included things such as rational bases or rational exponents would lead to difficulty. But what we came to understand was it wasn't the form of necessarily the number, or the number system rather, but really the inclusion of a negative sign in the expression. And so, thanks to my colleagues, I have to thank them for coming up with these catchy names. We labeled one which we called the sticky sign, and by that we're referring to students who are incorrectly attaching the negative sign to the base of an exponential expression. For example, the difference between the negative of 9 raised to the 3/2 power versus the quantity minus 9, that quantity raised to the 3/2 power. An extraordinary number of students saw those two things as being exactly the same.
And persistently through the groups?
Persistently through the groups. That was one of the indicators of a persistent error. And the other was what we were referring to as a roaming reciprocal. And again, what we're referring to there is confusion over how to handle a negative exponent. And what's very surprising here is it was coming up in a very simple expression. For example, 2 raised to the negative 3 power. We saw students interpreting that as minus 8, 2 to the 1/3 power, 2 divided by 1/3, and 3/2. So when you look at those expressions, you could see that students understood that a negative in the exponent meant reciprocation of some form, or flipping in a more colloquial way of saying it. But it seemed like they didn't know exactly what to flip, especially the students who wrote 2 to the negative 3 as being equivalent to 2 to the 1/3 power. Here they actually reciprocated the exponent rather than the expression overall.
So with sticky sign, you have the issue of the negative sign sort of in front of the expression, or whether it's attached to the base. And with the roaming reciprocal, you have the negative in the exponent, and so something is supposed to be flipped, but the students have this persistent error of not necessarily flipping the right thing. They're kind of just flipping something, but not in the way that we would sort of hope. So having identified these persistent errors, I'm wondering if there's a kind of a key issue that's left in your mind, or a question now that this raises for you that you want to pursue in the future.
When you think about the form of those two expressions, that is, those that are related to what we're calling sticky sign and those that are related to roaming reciprocal, they To us, they seem to indicate an underdeveloped sense of inverse. If you look at 2 to the negative 3 power, students don't see that necessarily as the multiplicative inverse of 2 to the 3. Nor do they see, say, negative 9 raised to the 3 halves as the additive inverse of 9 to the 3 halves. And so our conjecture in the paper was, well, maybe what the underlying cause here is this undeveloped sense of inverse. And so now what we're in the midst of doing is a follow-up to the study that we published, and whereby we try to answer that question a little bit more definitively. The way I look at it is, there are foundational ideas that a student needs to have some level of command before they can answer a particular topic, for in this case, simplifying an exponential expression. And so I tend to visualize that as almost as a chain. And so now what I'd like to do is say, well, where is that chain kinked or broken? What fundamental or underlying concept is preventing a student from mastering a topic such as simplifying certain exponential expressions?
And it makes me think, too, about a rule-based or procedural approach to instructing this content versus a more conceptual approach to instructing this content. Because, I would imagine with exponents, and as they get more complex, a lot of times the instruction is kind of rule-based, and at least in what I've observed. But that doesn't really explain why these certain errors persist rather than others, because if they're getting a rule-based, if they're taught the exponent rules for all of the different situations that you could see in an exponential expression, that doesn't explain why these two persist in a way that's different than the others.
Yeah, and I couldn't agree with you more. And I think we all have or have had the experience when we're learning an idea. When you're first learning with it, and you're struggling with some of the very rudimentary facets of a certain idea. We tend to. I'm just speaking from a personal point of view. I might struggle with those ideas initially, but as I start to learn more and I start to deepen my understanding, those rudimentary ideas become so second nature. They're no longer even thought about. They just happen. And I think, to some degree, that's part of what's going on possibly here. That students are stuck in this rule-based mode. But if they extend their knowledge to incorporate some of the structural aspects of the symbols that they're working with, it would help them in the long run when dealing with whether it's exponential expressions or any mathematical object.
Mm-hmm. And I think, what you just said, too, makes me think about a rule or having this sort of just a quick vision of what needs to happen is not bad, and in fact it's quite good if our students can get to the point where they see something and they just know how to simplify it or know how to rearrange it. But what you're kind of raising is that they might not be able to get to that automatic sort of speed or that automatic place if they don't quite understand the rule or if the rule doesn't make sense to them. And it sounds like, some of the rules for exponents maybe do make sense in a way and allow them to get to that automaticity or get to that ability that you're seeing in some of the later groups of students in your study. But something about these negative signs and the two persistent errors that you identified, maybe this rule isn't quite making sense to them, and that's why the rule doesn't really land home with those students, because there's something about these ones that's different in terms of the conceptual basis.
Also, if you look at it from the perspective of if a student starts to develop a stronger understanding by understanding the structure of the object, if they take an expression like 2 to the negative 3, and if they write that as something like 2 to the 1/3 power, saying it's equivalent to 2 to the 1/3 power, a structural understanding would hopefully have them question what they just wrote and say, wait a minute, could that possibly make sense? And if a student's working with an expression such as 2 to the negative 3, you can look at that in a strictly rule-based way and come up with an answer. And if they understand the rules well, hopefully they'll come up with the correct expression, the correct equivalent expression. But one of the things I think that makes understanding the structural approach powerful is that it allows a student to potentially go back and look at what they just wrote on the page and ask, well, does that make sense? Does it fit within the structure or the logical underpinnings of mathematics? And so a student who maybe has a very strong structural understanding of an expression such as 2 raised to the minus 3 might immediately look at that and say, oh, well, that's the inverse, the multiplicative inverse of 2 to the 3. And I know 2 to the 3 is 8. Mm-hmm. And so the inverse of that is, or the reciprocal of that is 1/8. So that should be the answer I'm getting. Mm-hmm. And so I think by incorporating that structural idea into their thinking, it allows them to go back and critically look at what they've have just worked on to see if it's logically consistent.
Mm-hmm. Yeah, I mean, some very interesting issues coming out, and I think too an interesting approach of looking across the groups of students and identifying these persistent errors, and it's kind of a methodology that could maybe be used in other topic areas as well.
Absolutely. I think we did this with one simple idea that came about through actually my interest in understanding how students work with logarithms and why do they struggle so much with both logarithmic expressions and logarithmic functions. And so developing from, I believe, from as early as possible, a structural understanding is important. And I know that'll get some criticism in the sense that, well, if you introduce too much rigor, you can serve, I think, more to confuse a student than to help them understand. And I would definitely agree with that. I think you first start with developing the rules, developing a very operational way of thinking. But what I'm not sure is happening is that the next step is being taken, and that next step being introducing a student to the structural aspect of the mathematics that they're using.
My guest is Rick Cangelosi from Washington State University. We've been discussing his article, The Negative Sign and Exponential Expressions, Unveiling Students' Persistent Errors and Misconceptions, which is in JMB. And Rick, before I let you go, I have one more question that I always ask, so I hope you're prepared. But it's just a question about imagining an alternative reality, and if you weren't in applied mathematics, if you weren't in mathematics education, what would you see yourself doing?
It's an interesting question, and initially it was, I'd say, it's kind of a difficult one to answer because I so thoroughly enjoy learning mathematics, and I so thoroughly enjoy teaching, and in particular teaching mathematics. It's hard to think of being pulled away from that. But if but if that's the ground rule, I would step back and say, well, what is it that I'm also fascinated by? And frankly, nature fascinates me, and I am so in awe of nature in all of its facets that I probably would have done something maybe in ecology, or I love the animals, and when I say animals, I have such a deep respect for life that even if there's a ugly spider crawling on the floor of my apartment, I don't squish it. I usher it out the front door. Mm-hmm. And so there's a part of me that I think if I didn't go into mathematics, that maybe I would have become a veterinarian.
Mm. And too, I mean, with nature, Washington State is probably just a very beautiful place to be.
Oh yes, we're in the midst of lots of rolling cornfields. Not cornfields, lentil fields and wheat fields. But it is a lot of farmland, and you don't have to go very far to see some very beautiful country.
Oh, great, Rick! Thanks so much for taking the time to talk about your work.
Well, again, thank you for having me. It's been a lot of fun.
Thank you for listening to this episode of the Math Ed Podcast. If you'd like to support the podcast financially, please use the PayPal donation button at mathedpodcast.com.